10,000 feet up, minus 40 degrees Fahrenheit. A critical lack of oxygen leaves the gunners completely helpless. They wear heavy, electrically heated suits to survive the freezing slipstream. The internal wiring fails constantly. The bulky layers restrict every defensive movement. Frost builds up thick on their oxygen masks, while their bare fingers freeze directly to the cold steel of hand-operated machine guns. How to protect the crew from frostbite and hypoxia? Engineers decided to build the world's first fully pressurized bomber. The military knew standard unpressurized aircraft had reached their physical limits. The Pacific Theater presented a massive new logistical nightmare. Distances were vast. Japan sat far beyond the operational range of any existing fleet. So, 2 years before Pearl Harbor, American planners issued a radical new specification. It ignored all current aerodynamic constraints. The new machine had to deliver 20,000 pounds of bombs across an ocean. 4 different aviation companies received the impossible parameters. The absolute requirement for cruising speed was 400 miles per hour. To carry 20,000 pounds of bombs into the stratosphere, the mission demanded a power plant of unprecedented architecture. Engineers introduced the Wright R3350 duplex cyclone. Its core survival mechanism was the exhaust-driven turbo supercharger. At 30,000 feet, atmospheric pressure drops. A standard naturally aspirated motor chokes, it loses thrust. The Wright engineers solved this by using hot exhaust gases to spin high-speed turbine wheels. This continuous breathing system supported a massive physical footprint. The engine block featured 2 rows of 9 cylinders sandwiched together, 18 cylinders. They drove solid metal propellers measuring over 16 feet in diameter. The motor achieved maximum power density. Those 18 cylinders delivered over 2,200 horsepower. This marked the absolute engineering limit for aviation radial engines of that era. The aircraft maintained target cruising speeds far above enemy interceptors. The spinning turbines captured the thin atmospheric wind. The impellers compressed the flow. Then the mechanical superchargers forced that dense, highly pressurized air directly into the firing cylinders. 2/3 of all B-29 losses during the war did not come from Japanese fighters. The bombers destroyed themselves. Mechanical failure caused the crashes. Pushing dense air into the cylinders solved the altitude problem. But it exposed a fatal aerodynamic flaw in the incredibly tight Boeing engine nacelles. Boeing engineers designed the cowling strictly for speed. The narrow profile minimized drag, but it choked the internal airflow. Cold wind rushed into the tight nacelle. It immediately slammed into the front manifolds. Since the front exhaust ports pointed directly forward, the incoming air absorbed the extreme heat before ever reaching the main engine block. This boiling stream then blasted the rear row of cylinders. The rear components overheated instantly. High-frequency vibration violently shook the engine structure. The red-hot steel exhaust pipes cracked under the relentless rattling. Blistering flames sprayed directly onto the cylinder heads. The intense thermal stress warped the moving parts. The engine swallowed its own exhaust valves. Catastrophic fire erupted in seconds. The Air Force effectively treated these massive power plants as disposable items. A standard round-trip bombing run over the Pacific lasted up to 15 hours. A brand new motor barely survived a dozen combat missions before heading to the scrap heap. The average operational lifespan in hours equaled 265. The engine firewalls offered absolute zero protection against a catastrophic thermal breach. Flight crews bluntly called these partitions tin pans. They melted in mere seconds. Even a drastically short engine lifespan could have been managed in combat conditions. But the chosen crankcase material turned a routine mechanical flaw into a death sentence. Why build a hot engine block out of highly combustible metal? The relentless obsession with weight reduction across the entire bomber program forced this exact risk. The engineering expectations seemed completely logical on paper. Magnesium alloy is 35% lighter than standard aerospace aluminum. It looked perfect for maximizing payload and fuel capacity. The reality was a nightmare. Designers had essentially bolted a massive pyrotechnic sparkler directly to a loaded wing. The physical sequence of destruction was violently fast. A stray spark spits from a ruptured exhaust valve. It hits the engine accessory section. The magnesium crankcase instantly ignites with a blinding white flash of pyrotechnic combustion. The self-sustaining chemical fire quickly reaches 5,600 degrees Fahrenheit. That is almost twice the melting point of structural steel. The white-hot blaze easily burns right through the tin pan. It directly torches the main wing spar. The massive internal aluminum structure loses all load-bearing integrity. The wing simply folds in midair. The bomber drops. Standard onboard fire suppression systems pumped carbon dioxide into the burning engine nacelle. The extreme heat simply broke down the gas and fueled the chemical reaction further. Engine fire extinguishers failed in 87% of all recorded cases. Theoretical calculations of combustion temperatures became a fatal reality on February 18, 1943. The second B-29 prototype carried a documented flaw. During its very first flight, an engine ignited. Eddie Allen, the top test pilot in the country, barely brought the aircraft down in time. Ground crews logged the fire. Program directors completely ignored the warning. Then came the 9th test flight. Allen took the heavy bomber up. The exact same engine caught fire again. Allen executed the emergency procedure flawlessly. He shut down the engine. He activated the carbon dioxide extinguishers. The gas hit the blazing magnesium and failed. Allen banked hard toward the Boeing runway. As the aircraft entered the landing pattern, a dull, heavy explosion violently shook the fuselage. The internal structure was failing. Radio operator Harry Ralston locked his microphone open. His voice cut through the static with a final report to Allen. The intense heat was melting the main wing spar. Burning components began shearing off over downtown Seattle. Uncontrolled flames tore through the metal bulkheads and penetrated the inner fuselage. The fire breaching the magnesium crankcase stripped Eddie Allen's crew of altitude and any margin for survival. At 100 feet, 3 crewmen bailed out, too low. Parachutes trailed behind them. The canopies never caught air. At 12:26 in the afternoon, the descending prototype sheared through high-voltage power lines. The massive airframe slammed directly into the Fry meatpacking plant. 5,000 gallons of aviation fuel detonated on impact. The dense, suffocating smell of burning gasoline and vaporized aluminum blanketed the entire factory sector. Why did the deaths of dozens inside a civilian facility disappear from the press? The government immediately enforced a strict information blackout. Sensors labeled the wreckage an unnamed military aircraft. 32 people died because of a documented, completely ignored engine flaw. The blast incinerated the remaining test crew inside the cockpit. The ensuing firestorm killed 20 factory workers on the processing floor. One firefighter died from severe thermal trauma the next morning. The multi-billion-dollar bomber program could not stall. Acknowledging a catastrophic design failure meant halting nationwide production and losing the air war. The War Department chose silence. They buried the systemic thermal vulnerabilities. They deliberately hid the extreme flight risks from their own incoming combat pilots to keep assembly lines moving. The military locked all technical data regarding the prototype destruction in classified vaults for 2 years. To stop crews from freezing to death, Boeing engineers divided the interior of the new aircraft into 3 sealed capsules. How do you save a crew from frostbite at 30,000 feet? Seal them inside isolated cylinders. The airframe became the first mass-produced bomber to feature a fully pressurized cabin. The engineering was strictly functional. 3 distinct pressure zones: the forward flight deck, the aft gunner section, the extreme tail. On combat missions lasting over 14 hours, this mechanical isolation was not a matter of comfort. It was the only system preventing mass crew fatalities from hypoxia. Outside the aluminum skin, atmospheric temperature dropped to -50 degrees Fahrenheit. Crews in older bombers routinely lost limbs to the cold. The new zoning eliminated heavy electrical heating suits. It eliminated freezing oxygen regulators. Men operated complex machinery in standard uniform shirts. But the central bomb bays required exposure to the outside vacuum. They could not hold pressure. To connect the front and rear crews across this dead zone, engineers installed a 35-foot connecting tunnel. The flight engineer unlocked the pressure hatch. He slid headfirst into the tight aluminum crawl space. A dull metallic hum vibrated through the casing. He dragged himself forward on his hands and knees. The narrow tunnel suspended him directly above the yawning abyss of the unpressurized bomb bays. One structural failure meant instant decompression. Most crew members could traverse this gap during flight, but not everyone. The tail gunner remained physically isolated inside his own separate pressure compartment at the absolute rear of the fuselage. The defensive network of this bomber obliterated 914 Japanese fighters. While the pressure cabin saved the crew from the vacuum, this radical grid protected the machine from interceptors. In previous heavy bombers, gunners froze at open windows, manually wrestling weapons against the wind. The new reality broke that mold. Men sat in warm compartments. Analog computers did the killing. General Electric engineered the central fire control system. It linked 5 remote turrets. 12 50-caliber machine guns armed the perimeter. The bomber functioned as a heavily armed flying calculator. A gunner simply caught a hostile target in his optical sight. He tracked the movement. The analog computer instantly took over. Deep inside the metal casings, physical gears and precision cams spun to solve complex differential equations of ballistics on the fly. Mathematics replaced human guesswork. The mechanical brain instantly calculated airspeed, gravity drop, and target velocity. Heavy servo motors buzzed aggressively against the hull. They automatically rotated the massive external turrets toward the threat. The steel barrels synchronously snapped onto the calculated intercept vector. The gunner just squeezed the trigger. Bullets met the target in empty space. The network featured absolute redundancy. If enemy fire killed an operator, the system bypassed his station. Another gunner instantly assumed control of the dead man's weapons. The defensive perimeter never dropped. Mechanical computation eliminated the flaws of human panic and poor visibility. The analog brain delivered a precise, unchangeable tally of destroyed enemy aircraft. 914. The aircraft's computing modules did more than track enemy fighters. They governed the primary weapon system inside 2 massive bomb bays. How to drop 20,000 pounds and not flip the machine in the air? Use an intervalometer. A simultaneous release of that critical mass would catastrophically shift the center of gravity. The bomber would instantly stall. It would snap into a fatal tailspin. The intervalometer prevented this. It turned the drop into a strict mathematical equation of weight distribution. But 20,000 pounds of explosives remained a theoretical maximum for short-range runs. Physics demanded a rigid trade-off. To strike the distant Japanese mainland, bomb weight yielded to aviation gas. Engineers integrated 7 interconnected tanks throughout the wings and fuselage. Ground crews pumped in 9,300 gallons of fuel for a single mission. Every extra bomb stripped away operational radius. Miscalculating this fuel logistics equation doomed multiple aircraft to drain their tanks and crash into the Pacific. When the steel doors snapped open over the target, the mechanism engaged. A bomb dropped from the forward bay, then one from the rear, then forward again. Workers drove every single fastener flush with the exterior metal. The surface became perfectly smooth. Zero aerodynamic drag. Beneath that sleek shell, the real complexity began. The intervalometer, the remote turrets, and the targeting systems demanded constant power. To feed them, engineers routed 11 miles of copper wiring deep inside the hull. Stiff wire bundles snaked through narrow cutouts in the fuselage bulkheads. The aircraft operated as a densely packed electrical organism. That exact length of cabling matched the entire power grid of a small 1940s American neighborhood, compressed into a single pressurized tube. 600,000 rivets. 13 tons of aluminum per airframe. 150 separate electric motors drove the internal mechanics, pulling current from 6 engine-driven generators. A standard crew could not manage this grid. Boeing built a dedicated flight engineer station just to monitor the voltage. Below that station sat the most critical hardware. The lower fuselage housed a built-in ground mapping radar. It found targets through thick cloud cover without visual contact. The War Department kept the technology strictly classified. Military sensors manually airbrushed the radar dome out of all official photographs. Engineers packed all those classified sensors, miles of copper wire, and 150 electric motors into a colossal shell. The airframe stretched out with a wingspan of 141 feet. That transverse span turned the aircraft into a flying steel building. What kind of thrust is needed to lift all this into the air? The machine's mass reached an unprecedented 133,500 pounds. That maximum takeoff weight made standard military airfields completely useless. Existing tarmac shattered. Army engineers had to design and pour entirely new, ultra-strong concrete runways just to handle the extreme ground pressure. The scale was absolute. These physical dimensions dictated a new operational class. The fuselage measured 99 feet in length. The older B-17 carried the name Flying Fortress, but this new platform doubled its structural weight. Boeing gave the machine a different designation, the Superfortress. Despite the heavy armor and massive payload, smooth aerodynamics kept the drag coefficient low. 4 radial engines pushed the heavy bomber past all previous operational limits. Maximum flight speed reached 357 miles per hour. The Air Force entrusted this 133,500-pound Leviathan to a highly specialized crew of 11. They climbed inside. Men locked themselves into isolated pressurized stations across the fuselage. 5 officers sat up front. The bombardier crouched low inside the glass nose cone. 6 enlisted mechanics and gunners secured the rear compartments. The internal intercom clicked. Static hissed. 11 different voices crackled over the radio check to confirm readiness. 4 massive engines fired up. Exhaust cleared. Outside on the concrete, 74 ground crew members stepped back in unison. Mechanics rolled away the heavy starting carts. Fuel trucks disconnected and cleared the perimeter. Assigning 74 technicians to maintain a single aircraft completely broke standard military logistics. Hosting just one combat wing of these machines required constructing a logistical base the exact size of a small city. The bomb bay held 4 times the payload of a standard B-24 bomber. But that unparalleled destructive capability carried a devastating economic penalty. Each airframe cost exactly $650,000. To fund this engineering leap, the War Department sacrificed the entire manufacturing budget of 3 B-17 bombers just to push one Superfortress onto the runway. By early 1944, Boeing rolled 97 brand new B-29 bombers off the assembly line. They were engineered to be the deadliest strategic weapons in history. But only 16 could fly. The rest were dead weight. Because testing, redesign, and mass production ran simultaneously on the exact same factory floor, the rushed process triggered a systemic engineering collapse. Mechanics opened the hatches of zero-hour airframes. The sharp stench of leaking hydraulic fluid flooded the cabins. Up front, manufacturing flaws warped the complex cockpit glass. Pilots looked through the panels. The horizon fractured into distorted lines. Behind the flight deck, pressure seals failed under basic test loads. Air hissed through the bulkheads. Fire control computers crashed before the engines even cranked over. The main wing structures demanded immediate external reinforcement. The electrical grid was a fatal hazard. Inspectors logged 580,000 faulty electrical connections across the fleet. That equated to roughly 6,000 critical wiring defects hardwired into every single bomber. The assembly line was essentially producing high-tech scrap metal at maximum speed. Deployment was impossible. 81 defective Super Heavy bombers sat rotting on the concrete. How do you fix a fleet of brand new bombers when not a single machine operates? You completely rebuild them by hand under the open sky. Rescuing these 97 defective aircraft required an emergency engineering operation. History recorded it as the Battle of Kansas. Over 1,000 technicians arrived at the frozen flight line. Temperatures stayed below zero. Mechanics tore open fuselage panels directly on the concrete. They stripped the factory wiring. They replaced defective connectors piece by piece. Hangars did not exist. Reassembling the heavy bombers outdoors in 5 weeks required tens of thousands of continuous man-hours. Crews worked in the freezing cold. Floodlights illuminated the tarmac. Human hands corrected the assembly line failure. Geopolitics dictated this brutal pace. President Roosevelt had personally guaranteed bomber deployment to China by the spring of 1944. This exact promise kept the Chinese army fighting. A Chinese surrender meant Japan could redirect millions of soldiers against American troops in the Pacific. Washington accepted 0 delays. The emergency overhaul worked. By the 15th of April, ground crews certified 150 aircraft as combat-ready. By May, Command launched 130 bombers on an 11,500-mile deployment flight to India. Those 130 aircraft heading to India were the physical embodiment of a radical blueprint. Spring 1944 rewinds to the drafting tables of May 1940. Boeing submitted the B-29. The architecture started with an extreme power plant. 4 Wright duplex Cyclone engines, 2,200 horsepower each. The deafening synchronous roar of 4 massive power plants hitting maximum takeoff thrust shattered the acoustic limits of the test stands. Performance targets dictated a total structural overhaul. The design demanded a fully pressurized cabin. Crews had to operate in the freezing stratosphere without oxygen masks. Standard aerial defense failed at such extreme altitudes and velocities. Engineers replaced hand-operated turrets with a computer-controlled machine gun network. No manual aiming, pure ballistic calculation. These technical specifications violently outpaced existing industrial capabilities. Boeing promised a heavy bomber constructed from hardware that barely existed. Forging these extreme theoretical concepts into operational aluminum consumed vast engineering resources. The first prototype finally achieved flight in September 1942, transforming that 4-engine, 2,200 horsepower schematic into an active fleet required the highest financial gamble of the war. The program devoured $3 billion. It absorbed 30% of the entire engineering capacity of the United States. Why invest billions in an aircraft existing only on paper? Because no other platform could physically reach the enemy. $3 billion in the 1940s equals $54 billion today. This budget exceeded the gross domestic product of several sovereign nations. The Manhattan Project built the atomic bomb for $2 billion. The bomber cost more. In May 1941, procurement officers signed the initial contracts for 14 test models and 250 production airframes. Officials inked the paperwork directly over blueprints of a machine that had never flown. After Pearl Harbor, the War Department doubled the quota. Standard aviation engineering dictates a strict sequence. Builders construct prototypes first. Factories begin mass production only after pilots resolve the critical flaws. The military discarded this logic. They ordered 1,600 experimental bombers before the first prototype ever broke ground contact. 4 massive assembly plants rose simultaneously across the country. The heavy, rhythmic roar of industrial presses echoed through the Boeing facility in Wichita, stamping raw duralumin into fuselage bulkheads. 1,400 subcontractors retooled their assembly lines. Tens of thousands of newly hired mechanics punched the clock daily. They fed a colossal supply chain for an entirely unproven concept. No other option existed. The United States military poured $3 billion into an unflown concept for one unforgiving reason. The physical limits of the existing B-17 Flying Fortress and B-24 Liberator made them entirely useless against Japan. It was an aerodynamic dead end. Fuel versus bombs. To strike a distant target, a bomber required massive fuel reserves. Fuel added extreme weight. To keep the aircraft from falling out of the sky, ground crews had to remove the explosives. Every extra mile of flight range devoured the payload. The specifications created a trap. The B-17 offered a practical radius of exactly 1,000 miles. Its bomb load peaked at 4,000 to 6,000 pounds. The B-24 Liberator pushed the distance further, but carried the same weight and lacked structural armor. These numbers worked for the tight geography of Europe. They meant absolutely nothing across the immense void of the Pacific. Then came the altitude limit. Both machines lacked cabin pressurization. Gunners tracked targets through completely open side hatches. Freezing, dangerously thin air violently rushed into the fuselage. Crews slowly froze inside aluminum tubes, fighting a war with open windows at 250 miles per hour at 10,000 feet. Overcoming that 1,000-mile radius was the absolute prerequisite for a completely new military doctrine. Engineers did not design the deadliest aircraft in history for aerial combat. They built an instrument to systematically erase entire states. 1938. The United States held a neutral position, but the intelligence data indicated an imminent global conflict. Germany rapidly militarized Europe. Japan actively waged a brutal campaign of expansion across China. American military analysts observed the expanding combat zones. They evaluated the mechanics of the coming conflict. How do you win a war purely from the air? You obliterate the enemy's entire industry down to the foundation. The tactical parameters shifted completely. Previous aviation doctrines focused on striking soldiers and artillery in trenches. The new blueprint bypassed the front line entirely. The crosshairs moved to steel mills, power plants, and the civilian workforce operating the supply lines. Planners assign this concept a cold, bureaucratic designation: strategic bombing. The sterile term masks the physical reality of total systemic destruction. You shatter the industrial grid. You sever the logistical arteries. You force a complete structural collapse of the enemy's military apparatus. Then, ground forces simply marched into the ruins to clear the remaining ash.